2.7. We are talking about linear equations still, but this is the last section in chapter 2, so we're going to be talking about intersections, or where lines meet. In terms of, you guys had requested for bolder highlighting. This is the best I can seem to do of all of the colors. So I'm hoping that pink is okay. So when we talk about finding intersections of linear functions, this is something that you've been doing on your calculator for a while. You've been able to graph it and ask the calculator to find intersections, but now let's actually do this algebraically, because you can do it with lines. So I'm going to give you an example. If we have Bobby drives to the store at 35 miles per hour, and Sarah rides her bike to the store at 10 miles per hour, but Sarah left 15 minutes earlier, when will Bobby pass Sarah, is the question. So if we assume that they both have constant speeds, and we start the time when Bobby leaves instead of when Sarah leaves, then we can build linear models for both, right? So Bobby is starting at t equals 0, and his speed was 35 miles per hour. So Bobby, which I'll mark by a B, is going to be equal to 35 times t for his distance, right? Using the models that we were talking about previously, but now in terms of figuring out when they cross, we have to compare those two models to each other. So I'm saying B is Bobby's distance, t is the time in hours, and S is going to be Sarah's distance. So Sarah left 15 minutes earlier, but she's moving at a speed of 10 miles per hour, right, as it says. So she's going to have 10 times t, but she's also going to have the additional distance that came from her leaving 15 minutes earlier. So I have here in parentheses t plus the 15 over 60, because she left 15 minutes prior. Minutes is not in hours, and I said the time is in hours, so I want to convert her 15 minutes to hours, and 15 minutes, there's 60 minutes in an hour, so that's 15 over 60 in terms of distance. So she travels at 10 miles per hour, so we multiply that by the number of hours that it takes her, and then we are adding the distance that she had already traveled before Bobby left. So now we have two linear models, and we have to go, okay, so when does Bobby pass Sarah? So he'll pass her when they've traveled the same distance. And since the output here is distance, then I need to set B equal to S, and so I have 35t is equal to 10t plus 10 over 4, which is the reduction from 10 times 15 over 60. From this, I just want to solve algebraically for t now. So I'll subtract 10t from each side, leaving me with 25t equal to 2.5, and then divide by 25 so I can isolate t. And I have t is equal to 0.1 hours. Okay, so 1/10 of an hour, which means that I would take 60 minutes and divide by 10 to get it in terms of minutes. So 6 minutes. It will take 6 minutes for Bobby to pass Sarah if they move at this constant speed, and he leaves 15 minutes after she does. If we take a moment to think about this graphically, right, so Bobby passes Sarah after 6 minutes. Both of them started, but she had initially already traveled some, so that's why Sarah's curve, which is the green line, has an intersection point that's not at 0, whereas Bobby started at 0. He's moving faster, so his slope is steeper, right? But he started at 0 and she started at 2.5 miles. So they cross 6 minutes in. And that intersection is going to be given at 6 minutes. We didn't actually calculate the distance, but we can. All we would need to do to determine that is substitute the 6 minutes into either equation, and that would allow us to then solve for the distance. So specifically for Bobby, for example, you would just substitute 6 minutes over the 60 minutes per hour into his equation, which was 35 times t, to get you the distance. We can use that now to answer question 2. So in question 2, if it takes only 5 minutes for Bobby to get to the store, how much earlier did Sarah get there? So we can find the distance to the store if we know that it only takes Bobby 5 minutes. So 5 minutes we convert to hours, so we have 5 divided by 60 because there's 60 minutes in an hour, multiplied by 35 because his equation was 35 times t, where t was in hours. That reduces to about 2.9167 miles. So if we know the distance, then we can answer the question, how long does it take Sarah? So, based off of when Bobby left, which means she still has the same equation, the same model that we built earlier, but we're setting it equal to the distance, that 2.9167 miles, or I'm going to keep the fraction 35 over 12 for simplicity. Divide both sides by 10, and we have 35 over 120. That's 0.29167 hours. Now, since it's such a long decimal, what I may want to do here is convert it back to minutes so that we can put it in the same context as the question's asking. And so given that, then I'll multiply both sides by 60 in order to maintain consistency, because there's 60 minutes in 1 hour. And then I have that 0.29167 hours is really the same as 17.5 minutes. So it takes her a total of 17.5 minutes to get to the store, but she left 15 minutes before Bobby, so if I subtract the 15 from both sides, then I see that she will get there in 2.5 minutes from when he left, and it takes him 5 minutes, and it took her only that 2.5 minutes from when he left. So that means that Sarah is going to get there 2.5 minutes earlier than Bobby, because it takes him 5 minutes and it takes her 2.5 minutes. So the difference between those two is also 2.5 minutes. So she will be there 2.5 minutes before him. So generally speaking, you're going to build the model and then solve it algebraically. You can still check your answers with your calculator, because you can still graph the two models and find that intersection point. But now I'm going to actually expect you to be able to do it algebraically in addition to that. A common application of this comes from supply and demand. So you may already be well familiar with this relationship because it's something that you would experience in daily life, right? We model supply as an increasing function because if we have more of an item, then we have more supply, right? And we model demand as a decreasing function because basically the number that we have is going to decrease as demand increases, right? Or if we have too many, eventually demand decreases because the system already has enough. So generally speaking, we have a form where the supply is given by y equals AP minus B. So P is the price of the commodity and Y is the amount you have in stock. And so for demand, that same amount that you have in stock is decreasing based on that price. So you have a minus MP plus D. As price increases, supply increases, and demand decreases, right? That makes sense. If something becomes more expensive, generally speaking, less people want to buy it. Now, what we're looking for typically with these supply and demand problems is what we call an equilibrium point. It is the point where your supply and your demand are equal. So you're setting the supply equation equal to the demand equation and trying to solve for the best price that's going to get you an equilibrium point. So we'll do an example with apples, because apples are something that you would buy at the grocery store regularly. So if you have a supply equation that's y equals 2x minus 1 and a demand equation that's y equals negative 2x plus 5, where x is the price of apples per pound, what is the equilibrium point? So I'm going to find that by setting my two y's equal to each other, 2x minus 1 equal to a minus 2x plus 5, right? Solve algebraically for x, so add 1 to both sides. Then I have a 2x is equal to a minus 2x plus 6, add 2x, and I have 2x plus 2x gets me a 4x, and then I still have a 6 on the right hand side. Now I can divide both sides by 4, getting me x equal to 6 over 4, which if I reduce that gets me $1.50 per pound. So I would get 1.5 from that, and that would correspond with $1.50 per pound because it's the price of apples per pound. So if apples are being sold at $1.50 per pound, that's a pretty optimum price to ensure that your supply and your demand are matched. Now, another question that we commonly have to ask here is there a price that will cause demand to be zero? Is there a price that is too high for these particular apples to the point where consumers just won't buy them anymore? That's what we're really asking. So if the demand becomes zero, all I need to look at is the demand equation, y equals negative 2x plus 5, and find when would demand, which is y, be zero. So 0 equal to negative 2x plus 5. Solve for x. Since the negative 2x is negative, I'm going to add it to both sides first, just because I don't like dealing with too many negatives, and there's a lot of room for error if I keep them. So I add the 2x to both sides. I have 2x is equal to 5, divide by 2 on both sides. X is then 5 halves, or 2.5. So the price for those particular apples that would make it so consumers would no longer purchase them would be $2.50 a pound, which I think we can all agree $2.50 is a little high, but we've seen Honeycrisps probably at the store for $3.99 per pound, and somehow they still get sold. So this must be an apple that's less popular. Real quick, conversely, we could look for, is there a price that's so low that we won't be able to keep them in stock? Is there a price that you could sell these apples at where they would be flying off the shelf to the point where they would no longer be in stock? So then we would look only at our supply equation, which was y equals 2x minus 1, and solve for when your supply goes to 0. So 0 equals 2x minus 1. Now the 1 is negative, so I add 1 to both sides, and I have 1 is equal to 2x. Divide both sides by 2, and 1 half is equal to x, or that corresponds to 0.5 or 50 cents per pound. So I've seen apples on sale for 99 cents a pound. I've never seen apples on sale for 50 cents a pound, personally. So this kind of makes sense. You don't see apples this cheap, so if you saw them on sale for 50 cents a pound, you would probably buy as many as you could reasonably eat in that period of time, just to save money on apples. Anyway, please let me know if you have any questions, and I'll see you in class.